Yep.
All right, I guess we can get started on that lovely note.
Go
Um,
ahead, Kevin. By
however,
the way, if I disappear on you because I have to have supper and also I have these 10 people as guests, please don't hold it against me.
it's all right. It's
Thank
totally
you.
all right,
Thank you so much, Kevin and Carolina, for this initiative. Thank you.
of course. So with that note, let's get started. Well, hello everyone. My name is Kevin George. I'm going to be hosting this introductory workshop to the Raspberry Pi. Um, Let me share my screen with you guys. So everyone's able to see my screen. Okay, perfect.
Yes, of course. Sorry. See, nobody answers.
No, I'm seeing some people in the chat saying yes, so that's great. Um, so this is our Raspberry Pi workshop for today. Um, so a lot of people have not heard of what the Raspberry Pi is, so let's talk about what it is. Uh, the first thing I want to talk about is how it's a computer. A Raspberry Pi is a computer. It's not just a confectionery dessert. It's a full-on computer, not just a computer, but a single board computer. So what this means is that although it would behave as a typical normal desktop computer, it's actually the same size as a credit card. Or in the case of you guess who ordered the kits, you have one that's smaller than a credit card. You have something that fits in two fingers of your hand. Very small computing um, in this small size. So that's one of the major advantages of the Raspberry Pi platform. Another advantage is how, the processor it runs. It runs an ARM-based processor. That's how we get that tiny computing and that tiny form factor. The RISC-based platform, reduced instruction set, is a smaller and more thermally capable per performance device. It's also lower cost. So you've probably, experienced this in your own lives with your phones and your tablets. They already have ARM-based processors in comparison to your desktop computers, which have 64-bit CISC-based processors or complex instruction set processors. So normally you'd see those desktop towers as being big and bulky, um, and they generate more heat, and it pales in comparison to what this platform is. Um, and another main advantage of the Raspberry Pi platform is its open source and hackability. So a lot of people like to use this to program projects, make hardware projects, and actually program hardware, which we will get into in a few moments. So when you get this device, you're going to notice that it doesn't have any housings or assemblies. It's just the pure circuit board as itself. So obviously you're going to want to handle that with care, keep it in a ESD safe bag. But it also is handy for if you want to, tinker around with it and make your own housings and your own projects with that. So moving forward, so this is not what, for those who got in the kit, this is not what you are going to see. This is what a lot of people have purchased for uh, their own projects. This is the form factor, the Raspberry Pi 4B, and the advantages are that it has a larger choice of which RAM size you'd want to get. It has a multitude of more ports compared to the one that you've got. So you can see that there's two micro HDMI ports, which both support up to two simultaneous 4K display out streams. So if you want, you can plug in two 4K TVs and run this small device off of that. And it's truly amazing how much performance for that can drive those displays. You can also see that this device comes with a headphone jack, two USB 2.0 ports, two USB 3.0 ports, which support up to 5 gigabits per second, and a full RJ45 gigabit Ethernet port sitting right there. So this is a full computer. This is the ports you can expect on any laptop or desktop computer, but again, in that small form factor. In on your Pi, the small form factor one that you've gotten with your kits, in addition to this one, you can see that there is a host of ports sitting above these row of male pins sticking out of the board, or in this case, female ports. This is what's called the GPIO, or the general purpose input output. So this is where the magic happens. This is where you're going to be able to interface your different hardware, such as your LED capacitors and your other electronics. This is where you're going to interface with your code to the hardware. So we're going to be utilizing this hardware in this presentation. So this small computer, it runs an ARM-based processor. It's in this small form factor. Well, it must be running a full desktop operating system. In part, that's true, because operating systems such as Windows are expensive and not open source. You typically would need like a license or a key, which would not make this cost effective. The most natural course of action is to have this run a Linux-based operating system and kernel. So it's very handy. There's a micro SD card slot on these devices, and so you can add your own operating system. In our case, we would want to run the default one, which is a modified version of Debian called Raspbian, or Raspberry Pi OS, as it's more modernly called. However, you're not limited to that option. You can use OpenSUSE, Chrome OS, Android, Ubuntu, Fedora, and a whole lot of other options for whatever you want to use for your projects or for your own personal use. And as I mentioned, that SD card slot is very handy for if you want to take out and load in your own operating system on the fly. So a little bit about Linux. The Linux operating system and kernel was invented way back when by a very smart guy named Linus Torvald. He had this idea of making his own open source operating system for the many uses of electronics and open embedded systems. Many systems such as cars and oscilloscopes run, even Linux. They run like a different version of Linux to meet that project end goal. So many entities contribute to Linux. So as it's open source, many people like to, contribute and add their own code and their own ideas into the main kernel. So universities, companies, and individual developers are who you typically see contributing to the Linux kernel. So because it's open source as well, people can, deviate and make their own version of Linux. So if they want to make their own specific use case for their own personal use, they can actually take the Linux kernel and operating system and build their own version of it and, own that for themselves. So we typically call this flavors. So many companies have made their own flavors. As I mentioned before, Ubuntu, Debian, and Fedora, or some of the most popular flavors out there. You also have like Mint Linux, Mint Linux, and Android. Android is a good use of the Linux kernel. They have different interfaces, feature sets, and different applications. So if loading these different operating systems, you probably would see a different interface for those. But underneath all of that, they all run the core Linux kernel. So although the interface is all different and the use case might be different, they all run that same underlying core kernel. So if that doesn't if you're not really understanding that concept, think about it as like the equivalent of shoes. So there are different styles and colors and designs and all that, but at the end of the day, they're still shoes. So just like that, this is the same concept that you can understand Linux off of. So because Linux was invented way back when, uh, before modern graphical user interfaces were really pushed out into the masses, uh, you most likely will see the command line interface. It's mainly command line interface based. So that's going to be the main user interface for Linux. There are most operating systems nowadays have graphical user interfaces, but they are stacked on top of the CLI instead of really coded in there. They're just a layer of on top of the kernel and operating system. And they are optional and they run on third-party windowing systems. Um, However, when we are working with the command line interface, uh, the language that we typically like to work with is called Bash. So, there are different versions of command line languages, but Bash is the most used one and the most adopted one used in Linux. So different commands such as ls for listing directories, cd for changing directories, rm for removing files and directories, and concatenate for listing the contents of a file. So these are the typical quote unquote commands that you will be seeing and using with the Linux interface. So because Raspberry Pi is meant to be friendly and open and welcoming, of course it will come with a graphical user interface. So this is what that will look like. You can see you have options for the menu. You have a Bluetooth icon, a wallpaper, very pretty wallpaper here in this case. You can see you have different accessories, preferences menus, and all those other things. So the different applications that it includes is the Chromium OS, the Chrome web browser, the open source version, of course, of the popular Google Chrome. It comes with Minecraft and other games as well, to play around with because this is a full computer and they can support that. It does come with programming IDEs, which we will be utilizing in this workshop. And it does have in the baked-in support for the GPIO, and also there's a header on the Raspberry Pi, this Raspberry Pi you got in this kit, as well as other Raspberry Pis called the camera serial interface, which you can plug in cameras and other accessories to take pictures, and or you can build your own camera. I've seen people build their own like DSLR cameras and taking very pretty pictures, and yeah, it works as anything you want. So that support for the libraries, those components are built in using libraries and built-in functions. And of course, that desktop experience is there, as well as a terminal in case we do want to work with Bash and the command line, as well as a full file explorer so that we can interface with our files and download files, delete, and make new files. So to start with, we're going to start by downloading and installing Raspbian and Raspberry Pi OS and using the Raspberry Pi OS, and then using electronic components such as I/O. For the purposes of this workshop, we are not going to wait to download an operating system. I will point you to the right direction. However, it is going to take some time for some of you, so we are just going to skip on ahead. However, I am going to show you where to get that, so you can go to raspberry.com. This is the official Raspberry Pi workshop, so website. So you can, purchase accessories or the Raspberry Pis themselves, download the software, and in this case, the Raspberry Pi OS. So there's different versions, different kernel with different kernel versions, as you can see here. There's light versions, uh, some with the full desktop experience, and then some with the desktop experience, plus that additional software. So what I'm going to ask you to do is to get the micro SD card that was included, get a USB to micro SD adapter or a micro SD to full size SD card and put that in your computer. What you're going to do is you're going to download this, and it's going to come as a zip file. So as soon as that's done downloading for you, you're going to extract that, uncompress that zip file, and then copy all the files to your SD card, safely ejected, of course, and then you're going to plug that into your Raspberry Pi, and you can get started with the setup process, configuring your language, your region, time, and all those other settings, and you should be up and running. For the purposes of this demonstration, I have loaded the Raspberry Pi OS onto a virtual machine because you are able to do that because it is a full Linux experience. So as you can see here, this is what Raspberry Pi OS will look like. As you can see, there are some minor differences. Like I have a battery icon here because I'm running this off of a laptop. But overall, I have the same applications, programming. All these will be included with your installation. You can get simulation software for electronics. It comes with a free Office applications from LibreOffice, and it comes with that Chromium web browser. So the full functionality, this is what I will be using for the demonstration. So the first things first, after you're done setting that up, is you're going to want to start at the terminal. So this is where we're going to be working with our command line interface, the bash language that we talked about here. And so what we can start with the first command we talked about. Let's oh, my screen froze. So I'm seeing in the chat, do we download Raspberry Pi RES for Windows and then put the image on the 4 gigabyte SD card and put it on the Pi? So what you're going to do is you're going to be on, oh, let me start sharing my screen again. So you're going to go to this page under software. You're going to go to Raspberry Pi OS. You're not going to go to this one. This is for if you want to download for your own computer, which you can do. You can also use this software for your own computer, but we don't want to do that. We want to go to Raspberry Pi OS, and then we're going to want to get Raspberry Pi OS with recommended desktop and recommended software. And then we're going to get that zip file. It's still downloading. It's going to take a while. If you want a slow connection, it's 3 gigabytes in size. You're going to uncompress that zip file, and then the contents of that zip file will be just shoved onto the micro SD card, safely ejected, and then put back into your Pi, if that answers your question. So we're going to be working with our simulation here. So this is what you're going to see. There's going to be already, if you go to the Raspberry Pi menu, accessories, and you're going to see terminal here. You're going to open that up, and this is what you're going to see. So in my, why is this not working? Sorry, hold on, this is not working. Okay, just had to exit the presentation. Now it's working. So in the presentation, we talked about a few of the commands, ls, cd, rm, and concatenate. So let's try those out now. So I'm here, I'm in my directory, wherever that is. So what we see here is our username and then the system host name. We don't really have to worry about that, but this is what we're logged in as. So currently, when you first start up a terminal session, it's actually going to start a session in your home folder. So when you open up the File Explorer, you're going to notice that you're going to be put into your home folder. So that's going to have your desktop folder, your desktop documents, downloads, music, pictures, and all that personal information. So the same thing with our terminal, it's going to put us in that directory. We're not going to know, but we can actually type in um, ls, and we can see that we've listed the contents of our directory. It matches up what we see here. So we have that bookshelf, our documents, our downloads, music, and all that shows up here. So that's a good indication that we are in this folder, and that's where we're working in for our commands. So let's say I don't want to stay in this folder. I want to work at the top level directory. So if you're ever working with a computer, you want to get access to the full file system. Uh, I want to get to this folder. This is just slash. This is the root directory. When I open up a hard drive, this is the first thing I'm going to see. So I want to be in this place. I don't want to be in my home folder. So what I'm going to do is I'm going to I'm going to change directory to this root directory, this first thing I get to it when I open up a hard drive. And then when I run that ls, that list command, I can see that I get all those folders and files right here. They all show up, the same exact thing as my file explorer show up here. So let's say, okay, what's the next one? So let's RM. So we can also manipulate, instead of just moving directories and listing directories, we can also manipulate directories. So let's say I want to make a file. I can use sorry, can you guys hear me? Sorry, I was having audio questions. So you can use um, the command touch, which is our bash command for creating new files. I'm in this root directory. I want to make let's make a text document. Let's call it demo.text. It's not going to work right now because we're in the root directory. This is typically where we host our operating system files, and the system doesn't want us to touch the files. So what we can do to circumvent that and to elevate our privileges is to run this in a super user do, or sudo, as most people know it as. This will override that permission denied because we are working in the root file system. So we can sudo and then rerun that command. And then hopefully when I refresh my page, let's go back. It's not showing up here, but let's see. We can see right here that our file is here. It's in our root directory. For some reason, it's not showing up in the File Explorer. I think it's just it needs to be refreshed. There we go. So I refresh the folder. Our demo.txt is showing up here. So we've successfully created our own text file. If I open this up, it'll open up in a text editor. test, and then I can save that as any other file, which this won't do in this case because it's locked. So we would need to run the elevation to edit that file, which I will do right now actually, so I can show you what we're going to do next. So the next command I want to talk about is the concatenate command. So we can, dump out the contents of a file by just running this command. So I can run cat demo text. I can see this is what I wrote beforehand. This is the contents of that file. So let's say I just want to get rid of this file. I can just type rm. We probably want to elevate our privileges since we're working in the root operating system directory. Rm demo text. So then I can refresh this folder. And that file is going to be gone. So we successfully created a file, changed directories, listed the contents of a file, just using bash. Does anyone have any questions before I move on? Someone asked, is this being recorded? Yes, this is being recorded, and this will be posted on the IEEE YouTube page. So definitely you can check that out anytime afterwards and get a quick refresher. Okay, if nobody has any questions about what I just covered, I'm going to move on to actually programming the hardware. So we can minimize this because we won't work with this right now. So we can open up one of our IDEs. I like to use the Thonny Python IDE. It's very beginner friendly. We are going to be working with Python for this workshop because it is very beginner friendly, and you can see that the interface is very, very friendly as well. And we're going to be using that to program our hardware. So we're going to make a new file here, and I'm going to save it I'm going to save it in our documents folder. I'm going to call it, the first thing we're going to work on is LED. So we're going to call it LED. It's .py for Python. It's a Python file. So we're going to use the py extension and okay with that. So even though this is just a quick introduction, we're going to be going through a little bit of Python, the programming language. So bear with me and definitely ask questions if you have them. So the first thing that we're going to work on is, like I mentioned before, the Raspberry Pi OS comes with the components and libraries necessary so that we can program that GPIO I mentioned. So these sets of headers we're going to be working with and we can program with. So we're going to use Python to manipulate this piece of hardware to manipulate an LED firsthand. So in Python, to use libraries, we typically import them. So I'm going to do that in this case. I'm going to use the function import, and the library we're going to be used called RPI dot GPIO. So this is our GPIO library on the Raspberry Pi platform, and we're going to call this into a variable as GPIO.
Oh, we can't see your screen.
Oh, my apologies. Let me. So now you can see it. So we're going to be manipulating this piece of hardware on the Raspberry Pi to manipulate our LED. So we in Python, we import our libraries so we can use them. And our library is going to be called rpi.gpio for the general purpose input output. And we're going to be calling that into a variable GPIO. We're also going to use the time library so we can do a little bit of timing with our LEDs. So import time. And we're going to manipulate this library to use the Broadcom, some Broadcom mode, because the chipset it uses is from the Broadcom company. So we're going to set that up using GPIO dot set mode GPIO dot BCM. We're going to, let's see what pin we can use. So when you're setting up this at home using the kit you received, you're not going to have a mail header. On yours, you would need to solder that on. However, what I'm doing with my kit is that I'm placing the Raspberry Pi onto the breadboard and then punching through the wiring so that they are going through the Raspberry Pi onto the breadboard so that they're making that connective connection. So in this case, how we're going to wire that up firsthand to the breadboard is we're going to have our voltage and our ground. We're going to hook up our 5 volts to one of the voltage rails. We're going to try to use the positive left-hand voltage rail so that it'll be easier for us to visually indicate. And then so that's going to be our pin 2. And then our ground, pin 6, is going to go in the right-hand rail so that we can see the negative terminal, the negative voltage indication. So that will give our breadboard a chance to use the Raspberry Pi's voltage, built-in 5 volts and ground. If you're using a smaller breadboard, you won't have to use any rails. You won't have the opportunity to use rails. You're just going to have to directly plug in the 5 volts and that ground into the available space you can use. But if you do have a bigger breadboard, I recommend using the voltage rails because that's going to make your wiring setup much cleaner and easier. I also noticed that in this Raspberry Pi kit, you weren't given a resistor as far as I know. So if you don't have any resistors on you, you're going to need a 330 ohm, at least a 330 ohm resistor to fully utilize the LEDs on this board. Otherwise, you are going to end up burning out those LEDs without proper resistance. Moving forward, that's going to be how our wiring looks up. So we're going to, for those with that set up the voltage rails, or you're going to get a 5 volt wire from the 5 volt rail into the positive end of your LED. And then you're going to have a resistor on the negative portion of your LED, and then that's going to hook up into your pin 6 ground voltage. So once you do that, you should see your LED light up. That's a good sign. That means the voltages on your GPIO are functioning fine, and we can proceed forward. So once you can verify that you can get a light out of that pin 2 and that pin 6, you're going to go ahead and move that wiring from pin 2, and we're going to use pin GPIO 4 in this case, which is pin 7. So this is going to be our programmable portion of our hardware. So we're going to utilize this specific pin 7 in our code. So we can use GPIO dot setup. That will be, I believe, 7. And we are going to designate it as an output because we are just displaying an LED. So that's going to be GPIO dot out for output. To visually indicate that our code is working other than the LED, we're just going to print a simple statement saying prints I turned on the LED. So I can't run this right now and show you because I'm on a desktop operating system. I'm not actually running this on a Raspberry Pi as of right now. But if you were to run this code at home on your Raspberry Pi, you should see that if you put in that wire from the positive end into our designated pin 7, you should see that our LED turned on. I'm going now. Once we turn it on, we can have a little bit of fun with that. So let's make it so that our LED blinks. Let's make our LED blink. So what I'm going to do is I'm going to have our code specify a time to wait to keep that on. So we're going to use the time library that we mentioned earlier, and we're going to utilize that here. So we're going to use time dot sleep, and we're going to give that 1 second. So sleep is just a function of our time library to wait until we do the next action. So in this case, we're going to have our LED turn on. We're going to wait 1 second, and then we are going to oh, I'm missing a piece of code. Hold on. GPIO outputs. Seven GPIO high. I'm seeing that some people are requesting that this is recorded, and don't worry, this again is being recorded and will be published on YouTube, and you can look at that at your own discretion. I know this is going to be a lot because the Raspberry Pi platform, Linux, Python, and then electronics. It's very daunting, but if you practice and utilize the hardware long enough, it will become a natural thing. Moving forward, we're gonna just add in this snippet of code before I put in that delay library. This will actually tell our LED to turn on. This is going to be in a high voltage state, so that means our LED will be given the full 5 volts, of course, going through the resistor so that it doesn't burn out. And now we can delay that. And then once we wait that 1 second, I'm going to tell our LED to turn off. So now when we run this code, you should see that, we should also put an indicator for telling you that I turned it off. Turned off the LED. So if you were to run this at home, you should see that your LED is going to turn on for a second. It's going to wait, and then it's going to turn it off. And then you should see some messages in the shell that says that I turned on the LED and then I turned off the LED. So that should be, if you're not seeing that when you do that, definitely check that you're using the right pinouts that you specified, and make sure that you're not getting any syntax errors. So a lot of you, especially incoming students who have taken FED, know that you have to build a traffic light project. So where I'm going to show you how to do that right now. In your kit, you should have a red, yellow, and a green LED. Once you have those proper resistors, the 330 ohm resistors, you can hook that up. And we can, so we've used pin 7. Let's use pin 11 and 12. So in my setup, I don't know why it's highlighting everything. And it froze. I don't know why it's frozen. Hold on, let me stop sharing for a second. Let me see. I think my virtual machine just froze. Wait. Let me restart my virtual machine session. Yeah, it looks like it froze on me. All right, that's fine. Let me start it up again. It's not a worry. Does anybody have any questions so far besides asking if we're recording this?
A quick question. If we were to say, if we wanted to say regulate the amount of voltage going through to the LED, we would have to use a potentiometer to do that, right?
Yes. In some modes, I believe you can adjust the voltage of just the GPIO. The GPIO pinouts, but for the static 5 volts and for the static grounds, you would have to use some other resistance, such as a potentiometer. So somebody just asked if this is a one-time Raspberry Pi workshop. Yes, this is just a one-time Raspberry Pi workshop. Again, if you need a refresher, this will be posted on YouTube. This is being recorded right now, despite the hiccups that are happening right now. Okay, my virtual machine just got back up, so I can share that session with you again. And I guess we're going to have to retype all that again, which is not a problem. So we're going to import RPI, GPIO, our GPIO library, doing that into one variable, importing our time library. We're going to configure and set up our GPIO mode. And we're going to GPIO dot, we use pin 7. Yeah, we use pin 7. Maybe it'll set up 7. That's going to be our GPIO output. We're going to print I turned on the LED, and then we're going to actually turn on the LED. Seven. We're going to set that as a high voltage digital state. We're gonna wait our 1 second. And then we're gonna turn it off. And I print, it could be lowercase too. Print, actually has to be lowercase in this case. Print, I turn off the LED. So that's where we were before. Now we're gonna start with our traffic light, quote unquote, project. So we're not gonna delete everything. We're just gonna start back up to our setup. Since we're gonna be using 2 more LEDs, we're gonna want to set that up as well. Somebody just asked, can I use any pin as an output? I get a runtime error. This channel is already in use. Continuing on anyway. What might cause this? So I'm assuming that you had all your syntax right. It seems like another program or something else is trying to utilize the GPIO, and you can't get access to it. If that happens, you might want to restart your operating system so that that GPIO access can be released back to you. So, okay, so we're gonna have 2 more LEDs. So let's do, what did I say before? I said pins 11 and 12. Let's do GPIO dot setup 11 GPIO dot out. We're defining the next set of LEDs, GPIO dot setup. We said 12. So that's gonna be 12 GPIO dot out. Okay, so how does a traffic light work? So when we look at a traffic light, we see that the red light is on for a longer relative to a short amount of time of seconds, then quickly turns to green, waits some time from there, turns to yellow, and then back to red. So we can simulate that output. So we're going to start with our red, our stop signal. So we're going to do, we're going to assume that 7 is red. I'm just going to put a little comment here that this is red. This will be our yellow. And this is going to be our green. This is not how you put comments in Python, but I've been using other programming languages today, so I'm just going to keep that there for now. So our pin 7 is going to be red, our pin 11 is going to be yellow, and our pin 12 is going to be green. So let's say I want to have our code wait. Our LED is going to be on first. We're going to wait, let's say 10 seconds. 10 seconds is fine. We're going to have our GPIO, the output 7, and GPIO high. So our red LED is going to be on. It's going to wait 10 seconds. I'm going to have it print a message as well. Time to stop. So after this 10 seconds, we're going to flash it to green. So that's going to be our pin 12 in this case. So then after this 10 seconds, I'm going to put GPIO, output 12, GPIO dot high. So then our green LED should be on. Let's also wait another 10 seconds because we want the cars to pass through. Actually, let me put a little statement here to print out and output. It's okay to go now. So the car is going to go by. We're going to have our LED on for some more seconds so that our cars can pass through. Then we're going to have our slow down light turn on. That's going to be our pin 11. So then it's going to be GPIO. That outputs. What was that? 11. That's going to be high. That's going to be time. Sleep. Then the yellow light usually stays on for I went up for 2 seconds. Let's have 2 seconds. And then it goes back to red. So that's going to be GPIO. The output 7 GPIO dot high. So then our red LED is going to turn on. You're probably, when you run this at home, you're probably going to see all of your LEDs turn on and not turn off. That's because I purposely forgot out the low statements. So after, just like in our last example, if you want to turn off, you have to turn off your LED every single time. So after our 10 seconds, our time to stop, let's turn off our LED. GPIO low. So then that's going to turn off. Then our other LED is going to turn on. 10 seconds. Oh, why is this so sensitive? Okay. There we go. GPIO output. Previous LED was 12, so that's going to be low. Wait 2 seconds. And then GPIO. But then 11. Oh, God, this trackpad. 11. GPIO low. Okay, let's go through this again. So our red's going to be on. Wait 10 seconds. Time to stop. Then our red LED is going to turn off. Our green LED is going to turn on. Let's print out, friends. It's okay to go now. We're going to wait 2 seconds. Actually, we're going to have this going on longer. 10 seconds for cars to stop. I think it deleted some code before. Okay, time to go now. Wait 10 seconds. It's okay, I'll reuse this. 12. Below. Yellow LED be on. Hi. Let's print out. You have to slow down now. And Time dot sleep. At 3 seconds. And GPIO dot output. Our red LED was 7. 7 is going to turn on. GPIO dot output. GPIO high. Okay, that's good. Our yellow LED is going to turn off. 11. GPIO low. So, assuming I got this correctly, this should execute a simulation of a traffic light in a shorter time scale, of course, and you should see those messages print out in addition to your LEDs turning on and off appropriately. Of course, you can scale this out by utilizing the many other GPIO pinouts and using some more LEDs. You can make another side of the traffic light that's opposite to what this is, and have like a fully working traffic system working. And you can build out your projects like that and scale them up. So that's working with our LEDs. The next piece of hardware that you should have got with your kit is a push button. So we're going to have our push button onto our breadboard. Of course, make sure there's a gap in between so that the pins aren't shorted. And so we're going to have one. We're gonna remove the other 2 LEDs. We're gonna keep 1 LED, but keep the wiring. You can keep a ground and a 5-volt ground in addition to one that's going to your GPIO. Hold on. Let me get a charger really quickly because I'm noticing that my battery is running low. Let me do that really quickly. Okay, I am plugged in, I am charging, we are good to go. Okay, back to our code. So we're going to have a one end of the push button going to 5 volts, or rather we'll use 3 volts for now because it's a small input we want to use. So we're going to plug it into our pin 1. Our pin 1 is going to go to a resistor to the one end of the push button. And then another end is going to go into, let's use pin 11 again. So let me see if I can take wire that up and show you guys how that's going to look like. So I know that was pretty confusing how I said that. The resistor. Then our ground. I said, what was it, pin 11? So that's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Where's the picture? Trying to send this picture to myself. Where's this picture? All right, never mind. It's not okay. I'll just have to show you. I have to Google the circuit for you then. Which one was I using? This one. This is what I was using. So yeah, this is yeah, this is the right one. So this is how you're going to configure your push button. So you're going to have 3.3 volts going to the resistor to that one edge of the button, and the other edge will be going into the GPIO, and that's going to configure your push button. So when we program that, I'm just going to load a new file because I want to save this for later. Once again, I'm going to call up that GPIO library. So I'm going to import RPI.GPIO. As our variable GPIO. Then I'm going to do import time. Then I'm going to do a GPIO setup. The pin we used was 11. That's going to be, instead of GPIO out, it's going to be GPIO in. Let me capitalize this. And then, yeah, that should be it. Okay, so once we have that done, we're going to use a control flow of an if statement. We're going to do if oh, the keyboard not working, GPIO dot inputs put 11. Let me use a brackets here to organize it. Equals to the equals to the value of high, GPIO high statement. We'll have it print out. Print, no, not capital. Print. I am being squished. I don't need to use curly brackets because we're working in Python. I do need to put an indent here. And somebody wrote in the chat loop. Right. So the way we do a looping statement, we could just quickly just say while true, which we'll also do in this case as well. So if we want to have something run infinitely, we just put while true, because true is always going to be true, so it will run indefinitely. So in this case, we're going to use that as well. So if you execute this code, and you push your button, you should see that in your console, your message will be printed out. I'm being squished. But we want to do more than just that. If we want to combine this with an LED, so an input with an output. So we're going to leave our code as it is now, but we're going to incorporate our LED. So we're going to introduce another piece of hardware as a setup in our code. So we should have been using our pin 7. So our pin 7 is going to be our GPIO out. And then print I'm being squished, and then we can do GPIO dash output, and over the 7 GPIO dot high. Time dot sleep 1 GPIO dot out put 7 GPIO dot low. So once you run this, you set up the circuit at home, you run this code on your Raspberry Pi, you should notice that once you push down your button, it will print out that message, I'm being squished. The LED is going to turn on for 1 second as we put here, and then it's going to turn off. So again, this is a very simple example, but you can scale this up by incorporating more LEDs, more buttons, more control flows, and you can get something very complex and very worthwhile. Instead of our LED, we have another piece of hardware in the kit, is our buzzers. So we can swap out the LED for a buzzer, and since it's already an output, we should already notice that instead of pushing our button and seeing an LED light up, we should see that a tone should be emitted from our buzzer. So it's also, you can use this to make music or play tones, alerts, I can see this as like someone building an alarm clock of some sorts, flashing the LEDs, playing a buzzer or tone to wake up in the morning, things like that. So that's the buzzer. The buzzer is just very quick and easy. It requires a little bit more voltage to play different types of tones, but I'm not going to get too much into it because it's just another output similar to an LED. What I am going to talk about though is the humidity and temperature sensor that was included in your kit. This is going to be our first piece hardware that's going to be really complicated to use. So, you're definitely going to want to look at the documentation for this piece of hardware. It is called a DHT11. It's a temperature sensor. You could build a lot of projects around that. I could see. I don't know, like say you want to monitor like the temperature outside near some plants, you can incorporate this, or you want to monitor the temperature inside your house, you can do that as well with this piece of hardware, and we're going to do that now. So you'll notice on your sensor, there's 3 pins. There's a positive, there's an out, and there's a negative. Um, so how we're going to do this is that we are going to, ideally, we're going to use the female to male wires that came in the kit because that's going to be the most easiest to wire up with. So I'm going to do that on my own here. I'm going to plug in, voltage and ground into and these pins are if you look on the sensor itself, they are labeled. So there's a positive, an out, and a negative. So in case you're having trouble with that, that's there for you. You can use that as a reference for wiring it up. So I'm going to wire that up myself. These wires are a little tricky. And how I'm going to work that out is that I'm going to plug the positive in to our, let's use pin 2, and then our pin 6 will be our negative, and then we're going to have one more extra pin out, and then we're going to put that into our pin 7. So we're going to remove everything that's on the breadboard now, the LEDs and the buttons, and we're going to replace that LED before with our temperature and humidity sensor. So the output, the out pin of that temp humidity sensor plug into GPIO4. I'm going to open a new file so that we can start programming that instead. So how we're going to do this is it's going to be a little bit complicated, so bear with me. The first thing you're going to want to do is you're going to want to get the DHT11 library. So just as like we use the GPIO library, we're going to be using another library for this new piece of hardware. The company called Adafruit, whether or not you've heard of them, they specialize in electronics, and they have their own electronic store. They also make the commonly used libraries for these common pieces of hardware. So we're going to be utilizing their piece of their library for our project. They have a GitHub, but it's going to take a little bit of time to install Git onto the system. So instead of waiting, we're just going to download a zip. I'm going to show in folder. I'm going to extract. By the way, once again, if anyone has any questions, please let me know. I know if this is going a bit too quickly, and you might miss a few things. So definitely, ask me any questions you might have. Oh, why is this not? Fine. I'm going to put this in my documents folder. I'm going to extract the zip file here. So if I go into my documents folder, it should be here. I want to make sure that certain library is here though. I think it's still extracting. Is it still extracting? Let me see. Did not extract. Let me see what's going on here. If it does, we'll override it. All right. I don't know why it's not working on my end, but I'm going to pretend it's there and we're going to program for it anyway. So we're going to go back into our terminal for a second. I want to have that open. But we're going to go back into our environment. And I'm going to import our built-in system. So this is our system library, so we can operate access parts of the operating system into our code. And I'm going to import that library as if I had it, but it's not working for my end. It'll work for your end. It won't work for my end for whatever reason. So, well, true. And with this library, I don't have to declare variables because they're already we can just simply do this. So this is a humidity sensor as well. So I'm going to program that. And I'm going to just declare that simply as our Ada fruits DHT read. What pins are we using? We're using 11, 4, print, or I'm sure is I'll explain this in a second. Our humidity is we might need a percentage here. Humidity factor. Then format temperature. I hope I spelled that right. Temperature. humidity. Okay, this should run. Let me indent that. So this is on a loop. Just want to make sure we're using the right pinouts. Okay. Okay, this should work out for us. So pretty much what I did is I told our library I declared the humidity and temperature variables to clip onto the Adafruit's DHT libraries built-in interpreter, and then I'm having it print out the values in this format. So it's going to take out the temperature portion and then the humidity portion in this variable state, and I'm also going to tell it to format it as a temperature value using this dot format for temperature and humidity. So once you have this wired up, and actually you don't need this terminal, you can run it here. So you can, once you run this code, you should see that in your console, if you know the environment is right and you have a strong temperature and strong humidity, you should see that the library is hooking onto the sensor, and then it is going to read the values from the sensor and then output that onto your console. So you can combine this alongside with the LEDs and the buzzer. You know, you can have like a threshold, and you can run an if statement. If the temperature is a certain degree or the humidity is a certain degree, you can turn on the red LED or the blue LED, or make a tone or buzzer. You can combine just the LED and the buzzers for that alarm clock project I mentioned earlier, or you can make any kind of project you'd want with more complicated pieces of hardware. You know, these GPIO pins are programmable, as we demonstrated here, so you can turn on and off certain things. They also support the I2C interface, so you can use it as a communication bus, and you can use different accessories as well. I know that I've used like some touchscreens, like you know, LCD, RPI. Like there are different like touchscreen attachments you can get for the Raspberry Pi thing that hook on to the Raspberry Pi, and you can use it as a touchscreen and interface with your desktop. And there's so many possibilities you can use this device for. And hopefully, you know, these examples give you some inspiration for what you'd want to do. And I wanted to ask one more time before we conclude the workshop if there's any more last-minute questions.
Would I be allowed to ask?
Yes.
Yep.
One question that I had about the looping in that traffic light thing, you know, how do you run that in a continuous loop? You know, red, green.
Right. So, as I think I did answer this before. I think what I answered was that you can use a while true.
Oh, sorry, I
statement.
missed that. I missed that. Yes, I missed it. And the
Right.
second one is the last program you wrote. you always use double quotes for strings, but then at some point you terminated after the percent with a single quote. Is that the way it is, or?
Oh, thanks for catching that out for me. The first one is supposed to be a single quotes. I mistyped that. Thank you for now now that looks better. Thank you for catching that for me. If there's no other question, sorry, did you say something? Okay. If there's no other questions,
Give the link for the YouTube would be available soon, hope.
right. So of course, with all our other workshops, we record our WebEx and we post it onto YouTube, and we do generate a link, and we post that in our Discord. So
Good.
definitely look forward to that, and it should be there within 24 hours, I'd say. I think the officers will put it up there. Other than that, if no one has any other questions, I hope that this workshop gave you some inspiration into making your own projects. I know this was quick and this was very nitty gritty, but again, you can rewatch it and you can practice on your own the different things and utilize different resources, and hopefully build some outstanding projects of your own.
Maybe set up a competition for the people who have already Raspberry Pi for proposing applications or ideas that they may get into to describe to others in the future.
Right, absolutely. Yeah, that is a possibility. I hope the officers will do. I will talk to them about that, and hopefully they can get that done either. No, we'll definitely next semester. Definitely next, because the semester is over. So next semester, yeah, till time flies. So next semester, hopefully they can do something like that. I will let them know. But other than that, that concludes my workshop. I hope that you learned a thing or two.
We definitely did. And
right.
we see that Brian Duemer is back.
I guess so, Brian. Hello.
That was nice to see. Yeah. That's
All
a very
right.
good job. Very good job, young man.
Thank you. All right. Everyone take care. Bye-bye.
Bye.